Morrison care of his mother, though he was only 3. James said to his mother, "Mother," he said he, "you must never go down to the end of the town if you don't go down with me." James Morrison.
I can hear you, so if that's any. Bear in mind, I can only hear the one with the microphone attached.
Yes, I understand. You know, it's funny you should mention that. Do you know that the hymns, the anthems for the services, the Coast Guard actually has one?
Yeah.
Who knew? The Merchant Marine has one as well. But we digress. All right. All right. You're going to give me the microphone so I can introduce you. We only have the one.
Do that, because otherwise it's all wired in.
All right. I'm going to be raising my voice and introducing Bill because there's only one microphone and we don't want to unclip it. All right. Welcome to the afternoon session of the Silicon Valley 4th Interest Group. This afternoon we're going to have a little teaser for an event that's going to be conducted in February. It's not exactly 4th, but it's in the spirit of 4th. To present this now and in February, unindicted co-conspirator of the early days of the 4th Interest Group, Bill Ragsdale.
Great. Thank you, gentlemen. Yes. Yes. Thank you. It is a delight to be here representing the Academy of Lockpicking Arts, and UC is established at our Los Angeles campus. We'll introduce the Academy of Lockpicking Arts. It was founded to provide training for magicians in the art of lockpicking. It started at a breakfast meeting, and it grew, and the Magic Castle sponsored it. It's now been presented 15 times for over 400 people. A local tour group picked it up, Atlas Obscura, and it's been done 5 times for Atlas Obscura. The first time we held it, it sold out in 4 hours, and the wait list was 128 people, and so it was presented 4 more times just working through the wait list. And the opportunity is that the 4th Interest Group will have that same 2-hour presentation, professional level, academically presented lockpicking. My name is not Professor Dumbledore from Hogwarts. It's Professor Bill Ragsdale. I'm the Dean of Instruction here at the Academy of Magical Arts. And I welcome you all today. We're going to have a great exploration. We will see the audio visuals, some of the support that's used in this presentation. The presentation is 2 hours long. It's multimedia. We do handcuff escapes. We do a trivia contest. We do simple lockpicking. We do some intermediate lockpicking. And those of you who choose may take home a complete professional set of lockpicks, a clear plastic lock, a CD of instructional material, and a 12-page cheat sheet. More about that later. So we will launch now into one of our introductory film. This is drawn from the internet, and it's 15 minutes of lock attacks. It's all sorts of lock attacks, many of which would be considered, opportunistic and non-professional. They are things that a locksmith really wouldn't do, but it's ways to get locks open. So without further ado, let us go into our lockpicking. Whoops, one ahead. This is Australian master key. Can we kill the lights? And put the camera up on the screen.
It's utilizing the 3 guiding principles of zeal, ignorance, and brute force. Why is this taking so long?
This is from Bosnian Bill on the internet. He has done 1,200 videos and he has 300,000 followers. Lockpicking has turned into lock sport, and it's actually an avid hobby around the world. So here he's attacking master padlocks, which is a master padlock number 3, which is kind of the low end of the consumer market. Lockpickers look at it with great disdain. However, some of them can be quite difficult. However, in this case, he's opening them up in about an average of 25 seconds apiece. The third one gives him a bit of a problem, but all the rest of them give up quite easily. He's using a pick called a Bogota, not anything to do with chili, but the fellow who developed the Bogota pick, that was his last name. And it's one of the more popular ones for quick access, and what they're doing here is raking. And he's opening these up, most of them in maybe the third rake or so in maybe 3 or 4 seconds. But that was about 2 seconds. You notice from a technology standpoint, they use 2 tools. A key does 2 things. Inside the lock are a series of pins, sometimes called tumblers. The lock positions those pins in a correct orientation, and it does the turning. In the case of lock picking, they separate the function. So one tool is doing the turning, the other tool is doing the pin positioning. This is very interesting. The metal they're using is gallium. Anyone here familiar with gallium? Anyone seen gallium? You know, gallium arsenide is used in LEDs. Well, gallium is a metal that's solid at room temperature. It melts at about 80 degrees Fahrenheit. So you put it in your hand, it will melt from the heat of your hand. Gallium penetrates the molecular structure of aluminum. So they take this gallium, put it on the lock. 6 hours later, it has permeated through the entire crystal structure of the lock. And intramolecular, it has broken the crystal structure of the aluminum. It takes about 6 hours and it destroys aluminum.
But that one said titanium. You mean they're not being honest with us?
It's a brand name. Titanium's a brand name. Like diamond.
Like my gold health plan? Is that made of gallium impregnated aluminum also?
Yeah. And the amazing thing is the gallium has penetrated the entire lock all the way through its structure from top to bottom in 6 hours. Think of the migration. Think of the velocity of migration atom to atom. And this is a lock that's very commonly used on storage units, storage lockers. It's round. It presents some security advantages. And of course, remember, a lot of these demonstrations are really exotic, and they're things that you wouldn't normally do. They're just trying to find a particular weakness. But what they find out is the center of that lock is made out of a material called Zamac. Zamac is a zinc alloy that's used for die casting. And almost everything you see out of zinc die cast is made from this. I think it's like zinc and tin alloy. But it melts at about 800 degrees, so the torch here goes in and takes the Zamac apart. Core of the lock melts out, and they open it with a screwdriver.
Is this what we used to call pot metal?
That's pot metal, same thing. Your Monopoly pieces, the little shoe and the little horse and the little thing, all the little figures on Monopoly were made out of the pot metal. And that core that you see of the master padlock is one of the items we'll be picking in February.
The heart and bolt is really rugged.
Well, yeah. Destroyed that.
Here's another technique called wrapping. It's inertial picking, because if you hit the lock with the right impact opposite the bolt, the lock will move forward, and of course the bolt is stationary, and the effect is as if the bolt moved back. So you tap the lock forward, inertia keeps the bolt back, lock opens. This one now is wrapping on steroids. And I'm even surprised it works. I kind of don't know how or why. There's only one bolt in the lock, but for some reason, it works. Building suspense. This one is cute. The fellow took the power transformer out of a microwave oven, and with copper bar made a one-turn coil. So the primary is 110 volt AC, the secondary is a one-turn coil. So the current goes up by the ratio of turns. So now what they do is in between the two electrodes, they're going to place a lock. And this is comparable to welding. You are doing essentially resistance welding in reverse, putting the current through the shackle of the lock. It's glowing red hot. Now it starts to sparkle. And of course the resistance goes up, and so it's getting hotter and hotter as the shackle narrows until finally it explodes and the shackle is now open and of course red hot. It's effective, but it's not portable.
It's amusing for demonstrations with a good pair of bolt cutters.
This is an ordinary Bic pen, Bic razor blade. And it shows you that the razor blade as made is actually essentially stronger than soft iron. This takes a long time. This has been slowed down, but I think they were probably working on this maybe 20 minutes, 25 minutes. But we've cut it down. He could have had a better screwdriver, a better vice grip pliers to hold that blade.
But it dulls the blade.
This is clever. This is could be used, can be used. If you were a maintenance man in an office building, this is the kind of technique that you might use, because it'll give you access to offices in the building if they lose the key. So it's a long steel rod with a fish line attached to it. Under the door, rotate up.
Now this is the far side of the door.
Now this is the outside of the door. This is the hallway.
You're now looking at the inside of the office.
I take it back. This is like inside the office, and the attacker is out in the hallway. Goodbye. This is commonly used by locksmiths. A locksmith will come in, and if you have a lockout, they may try to, first thing they'll do is look for an open window, but they don't like to do that because if they charge the customer $80 to come out and they go through a window, the customer feels very let down. But they might try for an unlocked window. The other way then would be try to pick it for a short term with an electric lock pick, maybe 3 minutes. And if that doesn't work, then they'll drill the lock and replace the core, because the core of the lock is worth maybe $11, and that's a lot less than the time that the person is spending. There are a set of jigs that are available so you know where to drill the hole. Given on the brand of lock, they'll have a little hardened steel jig that snaps into the keyway, and it puts the drill point exactly at the active spot. And notice you're drilling a little below where the lock rotates. And this one I like. I like this. The only reason the sound is here because I like the music on this. This is Dance of the Hours from Nutcracker Suite. It's a very advanced technology lock from Japan. I assume it's in production. It's very complicated. Very complicated. It has sidebars, it has wafers, and it has dimpled pins. Basically, all the technologies that are used independently have been combined into the one lock. And the animation is out of sight. And that is it for our video. Now, in the class that we're going to do, it's this lockpicking 203. We have 3 classes. Lockpicking 102 is a brief introduction. It's about an hour long, and it just covers the high spots. This one we're presenting is level 2. It's lockpicking 103, and it's 2 hours long, as I said, and it covers all the basic techniques. In addition, demand has caused our second semester advanced workshop, which is lockpicking 203. In that case, we go into techniques such as pin-by-pin picking, and we work on some vending machine locks, coin machine locks. So we're going to see now the process used in our simple picking, where we take a lock, go into the C-grip, put the turning tool in, a little turning force to the third finger, a rake goes in, a city rake goes in, and we lift and rock, and we're waiting for those pins to catch at the shear line. And if the keying is not too abrupt, not too high-low, this process will work. See that one more time? C-grip, very helpful. The clear plastic lock, see, we can see the pins inside. So this is a huge advantage. And once you get used to this, you should be able to open this in 10 or 15 seconds. If you then work at the lock from the end, it becomes a good bit more difficult, but you still can open the lock in maybe 30 seconds to a minute. In our class, the representation I make is that students will be able to open essentially all padlocks at the end of it. They'll be able to open up they'll be able to open up all desk locks. They'll be able to open up a lot of door locks and possibly some of the higher security padlocks. So this is skill number 1, which is simple picking, the basic introduction. Then we go to tricky picking, and every workstation here will have that clear plastic housing that carries 3 locks. The clear lock goes in on the left, and then you pick it from the end. Then you advance to the other lock positions. And the reason the class registration is limited is that we only have 28 of those assemblies. And if we have more than 28 people, then we'll have to double up. Here's an example then of what you see with that clear lock picking. The pick goes in from the side. You see the pins. The upper pins are moving up, down, up, down, up, down. They're catching at the shear line, and the lock opens. We'll show that one more time. The city rake goes in, rocks up and down and lifts. The pins tend to catch because of the turning force that's applied. When they're even, the lock opens. That rake, that pick incidentally is called a city rake, and it has a long, wiggly profile to it because it looks like the city skyline of buildings. And it's the handiest rake, handiest pick of all. 80% of what we do in class you can do with that one pick. Now we do desk picking. The center lock is from a desk, very ordinary wafer lock. It's used on industrial cabinets, desks, toolboxes, equipment, lockers, some padlocks. The nicest story on that was after one of my sessions, a student emailed me the next day and said, I got home from your class. We have a desk that we haven't opened in 4 years because we lost the key. And she said, and so then I opened it up. And that was immediately after the class within an hour or so. And here's an example then of desk picking. Turning tool goes in, city rake goes in, lift and rock. Quarter turn to the right, it's unlocked. Put the turning tool in, pick it back to vertical, so you pick it counterclockwise. There we go. So open, close. The next skill level is door picking. This is an ordinary Schlage lock. This is exactly like the Schlage lock that would be on your door, except it's been cut away so you can see the interior of the pins. The most popular, roughly the highest quality lock that's made in America. This then is a half diamond pick, and this is more pin by pin, where the pick goes in, it starts from the back, lifts the pins up, tries to catch, works toward the front. A little more to the front. You can kind of feel the pins catching. And of course, in this case, I could see where the pins were catching. Real advantage. There we go. And it's open. And with good technique, that's probably about average. That's about 30 or 40 seconds, something like that. Shall we see that again? So how much torque?
To you, it's
very light.
one by the tool.
Very light, very light. I call it a turning tool. The professional locksmiths call it a torque wrench, but turning tool is, intuitively more appropriate. Pins up in front, getting that back pin. One last pin in front. Bingo, open. All right, the next skill is padlock picking, and that is the master padlock down at the bottom, and we don't have video on that. There's no video on the master padlock. It's the same thing. So we'll do a little summary on this, and then we'll show you the takeaway at the end. People say to me, Dean Ragsdale, how do you get involved in lockpicking? What are your credentials? And I say, well, when I was 7 years old, I went into a shoe store with my mother, and I had a little padlock clipped on the belt loop of my Levi's. And the clerk said, son, he called me son for short, he said, would you like to learn how to open that lock? And I said, well, what 7-year-old wouldn't want to learn how to open a lock? So he showed me how to take a little bobby pin, bend the end a little bit, put a hook in it, into the lock, trip the mechanism, unlock the lock. When I was 9 years old, my grandfather showed me how to make a key to a lock. We took a thin strip of brass, fit it to the shape of the keyway, smoked it with a match, put soot on it from both sides, put it in the lock and wiggled it. Wherever there was a mark on the soot, we took a narrow file, filed away. And that got past the warding or the barriers inside the lock, and the lock opened. When I was 15 years old, the next door neighbor passed away, and his wife gave me all of his books. He was a locksmith. So all of a sudden, I had a 20-year history library of locksmith ledger and manuals and books, which I devoured. When I was 19 years old, my summer job was with P.S. Bible, who was a mobile locksmith. He had taken a Muni bus and outfitted it with bunks, a kitchen, and a full 2-bench locksmith shop. And we drove coastal California from Moss Landing on the north to Arroyo Grande on the south, spend typically 2 days in each town. We would go to towns like Chular, that were way out in the boondocks that had no locksmith nearby. San Miguel, California, Atascadero, California. So that summer, up and down the coast. The next summer, I came back to work for him, and we then did the western side of San Joaquin Valley. So we started around Chelam and worked south down to Traft, Hanford, Pixley, Reedley, all the little towns, again, that had no locksmith. He would show up, put out his sign, "Lock keys made here," and the people knew he was on a route, and they'd come and they'd bring their stuff to him, or they would call him and he would go to their home. That second summer, he then said, "Bill," he said, "you're doing so well in all of this." He said, "I'd like you to meet the man I consider the world's best locksmith." So I don't know if he was the world's best locksmith, but he was the fellow that the other locksmiths brought stuff to that they couldn't handle themselves. So he and Bible, this P.S. Bible, had been friends in Bakersfield, California during World War II. So for 3 days in Las Vegas, these two gentlemen sat around and drank coffee and reminisced about the old days back in Bakersfield. And then I took the service calls. So I knew nothing about Las Vegas. They gave me a city map and the call slips, and then I went out and did service calls around Las Vegas as a quick introduction to the city. The next summer then, I went to work for the gentleman in Las Vegas, Slim Ewing. He ran Ewing Manufacturing, and his core products were high security products for the casino industry. So we made Keno boards, we made slot trays, we made check trays. We sold a complete casino arrays of dice, checks, cards, everything. And he had invented the drop box. Now the drop box, you probably know, is that metal box under every gambling table. The dealer shoves your money through a slot in the table into the drop box. Before Slim came along in 1948, the handling of drop boxes was totally insecure. There was easy theft out of those drop boxes by casino personnel. Slim Ewing came up with a double lock box. It was metal. When the box is locked on the table, it takes a key to take it off the table, and when you take it off the table, a slide goes through, closes the opening, so the box is totally sealed, and a different key is used in the counting room to get the money out. And that was used exclusively in Nevada for 35 years. Slim, that was his key to fame, and he knew all the casino people, he knew all the casino owners, because they all used his drop box. After that, I went to work for Lawrence Livermore Lab, and for 7 or 8 years I shot off atomic bombs down in the Nevada desert, but that's a different story. After that, my wife and I started a company doing, of all things, electronic door control. Since I was an engineer, we said, let's do it electronically. So we came out with an ID badge reader. It was sold internationally by Honeywell Corporation as their standard product. It was on some 1,200 jobs around the world, and including about 15 of the major airports. So it was installed at Kennedy, LaGuardia, Newark, New Orleans, Wisconsin, San Francisco, SeaTac, Sky Harbor, and to this day it's still in use at Kennedy Airport, and 3,000 doors under control in Denver International. So that was, and this was all programmed in Forth. So we were 100% Forth shop. Andrew McEwen worked for us as programmer, and he was F83 or Winforth 83 is Andrew McEwen, and he began his work with us 100% in Forth. When Honeywell would come to visit us, we would take the Forth books and we would turn them titled down on the bookshelves. So when they walked through and saw our plant, they didn't see the word Forth on the back sides of books, because we didn't want them to know why we were able to do such responsive software so effectively. And in conclusion, we have a goodie pack take-home. The take-home pack has in it the clear plastic lock, you see, and it has a set of lock picks, and it has a DVD and a 12-page cheat sheet. Now, there is no cost to come to this workshop. Normally, it has an admissions fee of $50, and you get to take this kit home. But as a one-time only basis for the fourth interest group, anybody who attends and wishes to buy the take-home kit is $20, and we'll have enough for all those that wish to do it. So we'll have a loaner set that you use here. We'll have a take-home set you take home.
You take them home today or a big box?
In February. Take home in February. If you have your own tools, your own lock picks, things like that, by all means bring them. All are welcome. No difficulty at all with that.
Will you be able to take credit cards or cash only?
There's a survey card that has been passed out, and we will take cash, check, PayPal, or Venmo. And there's a line down there to write other, so if you had something other than those four choices, any of those are good. Happy to do it. So if you if you have a PayPal receipt on your cell phone, just come here, flash it at me. I'll see the receipt, and you get the take-home kit. It's professional grade picks. Several have been modified by me for utility, so it's an enhanced set, somewhat better than actually comes out from our dedicated factory, which is in China. So that concludes my formal remarks. It is a delight to present here. And are there any questions? Stunned silence. That's very good. Thank you very much. Thanks for the use of the hall.
Is there anybody not willing to admit to showing up for this? All right. All right. Do you accept the Anglican Church or not? It's one of those things. All right. Here's how. For Bill.
What?
There's another safety-inspired lock-picking store. There's a bicycle locks that found out that and hole diameter to fit in the bike lock to unlock it. Are you familiar with that?
Yes. Again, if you look on the internet, good old YouTube, with Bosnian Bill and another fellow called the Lockpicking Lawyer, they have an infinitude of lockpicking examples, including the Bic attack on the kryptonite bike lock. You just put it in, rock it, and you crush the plastic. Where the pins are stiff, the plastic crushes away, and you end up making a key.
Right.
Yeah.
As if by magic. So here's how this is going to work. Since we need to be pre-registered, we're going to have a one-time only meetup.com commitment. If you're not on meetup.com or you don't want to do it that way, you can send me an email. The meetup event is going to have a notice that says, if you don't sign up for this in advance, you may be turned away. And that will allow us to not get mobbed by folks who just show up. It reminds me of this guy from last year who was talking about quantum computing. We had a number of people that we had never seen before or since, and I think that was great. But if you had double that many, it would have been a problem.
Yeah, well, the reason that was is I advertised it at Stanford events.
Exactly right.
I actually got some people.
And if it's like 2 weeks before, it might be a good idea at that point to also advertise this at Stanford events or other, and we'll.
Are you planning to have this event at Stanford?
Here, yes.
Here, on the
February meeting from, I think, 2 to 4 suits me because we would turn off the stream, and I'd rather do that at the end of the meeting rather than, turn it off till 2 and have it from noon to 2.
Oh, Bill?
One question. You got 6 different tools there. Are they different for different locks, or they all work similarly with all locks?
Okay, Dr. Ting's question was the different shapes of the locks, are they there for different purpose? Let me make the first observation, and that is that 3 major worldwide brands of lock picks, actually maybe 4 or 5, they get fancy names, they're different shapes, they're different handles. Like so many shiny objects, as you know, lures sold to fishermen are to catch fishermen, not to catch fish. Well, fancy lock picks are meant to catch lock pickers, not open locks. Now, the ones you see up here on the screen are the minimum, standard, simple, basic picks, and they will do 90%, 95% of all lock picking. And they're identified normally by their shape. The top 2 are hooks. There's a shallow hook and a deep hook. The third from the top is a small half diamond. The next one down is a large half diamond. And then comes a snake rake. It has a little wiggle in it, kind of like a snake wiggling tail. And then the bottom one is a Bogota, and it has a kind of a sinusoidal shape to it. And that shape is really the most useful generally. In other words, I would use that about half or 60, 70% of the time. Only if you get into difficulty do you use those other ones, because first you try mass picking all the pins at the same time by lifting and wiggling. Then you try group picking, where you use the tip of the pick and you try to get 2 or 3 pins at a time. Only then do you use those hooks or diamonds where you go 1 pin at a time. Every technique you use takes about 5 times longer. So when you go from raking, which may be 20 seconds, when you go to group picking, it might be 1 minute to 2 minutes, 3 minutes. When you go to pin by pin picking, it might be 2 to 5 minutes. And if the lock is major difficulty, you have no assurance you will open it up. There's no assurance. My son had a storage locker and called me in on it, and I brought the tools out the first time and attacked it, and I was on it like 8 minutes, and I said, no, I'm not getting anywhere. I'll come back tomorrow. So I came back the next day with an electric pick gun. And with the electric pick gun, you go in, and it still was kind of difficult, but the pick gun got it in maybe 1.5 minutes, something like that. But some locks are set up with special pins inside or in such a way as to try to countermeasure picking. And there are reports on the internet, you'll see people talk about, oh, I had an Abus 1200, something very difficult. It took me 4 days before I could get it open. Now, I don't have that kind of patience or difficulty. I would go on to something else. Any other questions?
All right, thank you, Bill, and we'll see you in February. So once again, we'll be using meetup.com to register. We're going to promote on Stanford events if we don't get a good response, if it suits Dave to do that. We're going to take a short break.
And also, you will get a personalized memento. So by registering with your name, you will get that personalized memento at the event. So that's again why we pre-register.
What's that?
There was a portion you wanted to do with the video turned off.
Yeah. So,
You should have let me know.
okay, so
You let me
what?
stop broadcasting.
So I'm going to talk for about 30 minutes. I have an hour, right?
By the way, we're broadcasting now. So.
Okay. Yeah, I have an hour, right?
Does he have an hour?
1 hour to talk.
Look at the schedule I have done.
Oh, yes, what do you want to know?
How long does he have?
How long does he have? From 1400 to... There's a warm-up here that I don't understand. What's the warm-up?
What the hell happened here?
Roughly what ballpark are we talking?
Oh, I see what's going on. That's weird. I never saw that before.
Nice.
Yeah, I guess. So what I want to do is I want to talk for about 30 minutes, and then I have a 30-minute video, which I haven't even seen. Our president from Made in Space is going to talk about the future of... Yeah, okay. No, this is going to be... This you can stream. After the video, we'll go to live.
But you have no time. Trying to think of the safest way of doing this that doesn't jeopardize our ability to have SVFIG.
professional activity. It's kind of like amateur, like so amateur practice medicine.
I think that would be okay because, you know, people don't know what it is.
Then again, people don't know what it is. So the problem is, how do you do it?
Well, you know, you're welcome to advertise anywhere you see fit.
Point at the meetup page.
Yeah, they might not search for that keyword, block sport, but, or, they may not them, but they, anyone already knows what that is, so probably.
Right.
Well, you know, what if the public face from the big standpoint says everything except Stanford, and that it's implied, that people would be implied to know this consent, and to not have any association with Stanford, because the big people will know where it should be.
Well, it has the menu for all the other stuff that goes on there.
No, separate event. Meetup.
Oh, okay.
Only it won't have the venue, it won't have any information other than here's where you sign up.
But people who, so in meetup, there's a group of members, SVFIG members, who created that, and if you do it under another,
Organization.
yeah, so.
Used for that purpose.
But maybe
Maybe an SVP they can announce to them, won't have a venue,
Not on meetup, but
one
on,
meetup.
email, SDG, or.
Yeah, you don't have to, every time I put in an event, you know, it doesn't have, the way I get that in is I just copy the last. At one point I had to type where it's gonna be. And instead of the venue, it will be contact, you'll be contacted with the venue.
well, is there?
No, there's several Facebook, but none that I know of meetup.
Well, we'll look before we.
This is actually just for comparison's sake. This is on Airbnb. Not just because in LA we were, group I worked with, Amazon Secure, they were looking through Airbnb. Airbnb books, not really book places to stay. I would navigate going through Airbnb. Okay, so
Right.
I think you can advertise in any way you care to, but not tell where event it is.
I have a line that maybe we could put something with coming attractions, contact me by email for details, for January. For February, nothing special event, no screening. And then on the mailing list, we can promote it till we're moving things. Well, it brings back content. Only in February, unless you want to give them a little extra, it'll ship you one, right?
So I
No?
prefer.
Not that business, okay.
Shipping is.
Well, you can go to Amazon or, what is it, Banggood?
But no, you go on eBay, I can buy a set for about $18 on eBay. But they don't have the DVD, and I have polished 3 of the picks a special way, and they,
You won't get those until February. But if you really did set on how you, is it Banggood? Is the Chinese Amazon?
AliExpress.
The seller, like, I want to say it's Banggood or something like, some word like that. Amazon, eBay, or just random. Internet.
everything comes with a clear padlock, and that's the same company.
Yeah, pretty much everybody makes the same thing.
I just want to, say once again, my concern is that
some rule about possession of burner tools.
No, it's, well, it's, you tell me like burglary tools is in conjunction with a crime. It's always in conjunction with a crime.
Well, you know, there's a lot of different charges called crimes that they can basically arrest you for. It's sort of like arresting you. The common charge is called contempt of cop. Because they want to haul you.
It's fair to say, Dave, your concern is less about legality and more about just, we're here at the humor.
You don't want to make them any badder than they
I
are.
just don't want to draw any attention at all. Because, you know, there's always somebody that will say, it's wrong.
How do you feel about doing it maybe off campus, getting a room at a pizza place or something? I don't know. It's been years since I've looked into any of this stuff.
I'm not sure that's necessary. But if that's,
I'm going to turn the video off.
yeah,
So turn the video off. It's not going to be on the February agenda. It'll be a separate event on Meetup. And people will only be told the venue if they're actually coming to the event.
Right.
Is that going to be enough for you?
well, I was thinking maybe after they register.
Yeah.
Yeah.
They're actually coming to the event. That's what they're saying.
And I would say the agenda item can be very obscure and say returning the video
Well,
off.
that's all it's going to say for February. Special event, no streaming, blah, blah.
Exactly.
Thank you for sharing.
So,
Okay, that's what I want to hear.
All right. Yeah.
Well, no, it's whatever to cover with, but either way, it's fine with me.
It would be okay to sell the tools here, but don't.
No, we don't have to like anything sold, they don't
We're selling
know.
donuts.
Yeah.
We're selling donuts. But that's a donation. If that even is just marketed as a donation.
I've been actually lying about that we don't have, money to serve food here.
Right. I suspect you were. Yeah.
And I have one more thing. I have to mention is that the rules for this room will change a little bit for next year. In the past, I've been able to reserve the room, officially.
I'm fine.
More restrictive policy.
Are you ready?
You're right.
I like it when I'm standing about 12 feet away
And so now,
and the clerk comes up to the counter and basically gives you the impression this time is so important. Order that. Ready to order? Yes, I always stand 12 feet away from the counter, looking carefully at the menu, trying to read it. Well, now I want your opinion about my being ready to order.
certified bartender.
Yes. Are you still looking at
Yeah, he's responsible.
Yeah, that's right.
For you, looking at liability.
And that costs $900.
Hey, Kevin, can you turn the front lights down so it's easier to see the screen?
So no idea. First
I thought you did it before. Is it here?
No. Here, let me have a chance to screw it up. All the way down. So there's no.
I thought somebody walked in the back and turned it. Oh, there it goes. No?
You're getting them down. There you go.
Yeah, we had
There you go.
we had a house set up. And we had all the time. There was some
All right, do you feel like we're in the ready to go mode here?
Yep.
All right, now if Dave stops talking, come.
stood up for us.
Don Golding here. work at a company called Made in Space, and we're going to be talking about that a little bit later. First, we're going to talk about the board project. So I'm going to be talking about AI, the AI bot project, which is a board project. I'm going to do a quick talk on System Verilog, and then we're going to talk about FPGA AI controller kind of briefly. And then the last 30 minutes, I'm going to show you a video, which I actually haven't seen yet, but I heard raving reviews for. Our president, Andrew Rush, was on a space panel, and he's talking about the future of manufacturing in space. So it should be a very interesting video. It's about 30 minutes. So, the dream was, this is a SOM, System on Module. It's got a reset pin. It's got RS-232. You talk to it and you program it. And it's supposed to be easy. Never had so much trouble programming a microprocessor in my entire life. So our issue was, and Brad worked very hard on this. You know, he installed all the tools, all the factory tools, and once out of 20 maybe it would flash, and only on certain boards. So that kind of tells me there's, you know, some sort of noise problem. The reset isn't conditioned properly, some other things like that. So this is the original circuit. When I started, I used some pretty important pins for I/O. I/O 0, which I did do correctly, and there's a jumper, and that forces it into the flash programming mode. But turns out I/O 2 also should be low, and then I/O 12. So few gotchas on this chip. So this is from the F32 manual. We can see that GPIO 0 and 2, actually I have a laser pointer. I guess I should use technology here. So I/O 0 should be 0 for download. I/O 2 should be don't care. Now I/O 0 is the one I have that jumper on, so that's correct. Then we have enabling, disabling, debugging, log print, and this is pull. I think that's GPIO 12. So anyway, you have to. These are bootstrapping pins. They have to be in the correct setting when the thing turns on. Another little tidbit. So there's a hardware design manual, and it talks about how there's 50 megahertz noise coming out of the TXD pin, and they recommend a 499 ohm resistor in series. I mean, good grief. So anyway, I'm doing another board spin. I'm making these changes. I'm going to add that. Reading about the reset line is actually, it's very picky. Now I got this from I believe it was the ADR Fruit board is where I got my core circuit from, so I'm just like amazed it didn't just work. But anyway, they used a simple resistor cap on the reset pin, which means that it's going to drop to 0, but it's going to slowly ramp up, right, depending on the RC time constant. Well, that's not, and the pin, of course, they made it, you know, with as an analog pin with the thresholding voltage at some point. But I experimented with increasing. So originally it was a 1K and a 0.1 mic, which is pretty fast. And some people said, well, you know, increase the 1 mic cap to 10 mic. So I tried that, and I tried a 10K resistor, and I also tried a 47 microfarad cap, which it didn't work at all. So I tried different things as far as changing the RC time constant. and it just wasn't reliable. So I'm going to an actual circuit now. This is a power on reset circuit. It'll give a very nice clean square wave, and based on the RC time constant, we can set the square wave to whatever we want. You know, it could be a millisecond, it could be 963 microseconds if it's that picky. So anyway, we'll have a digital power on reset. So going forward, I'm going to make the schematic changes already started. Then I'll make the PC board layout changes, and I think this time I'm going to be smarter. I spent $1,000 on that first board spin, which they're basically all scrap. So what I'm going to do this time is I'm going to make 20 raw boards, which are pretty inexpensive. It's like $60 or something. This presentation mouse is sort of doing its own thing. Come on. So what I'm going to, I have a board stuffer down in Santa Ana that's pretty reasonable. So I think what I'm going to do this time is I'll have 4 boards, and I'll just populate the CPU and the reset circuit and that, and we'll make sure that we can program these parts before I have the rest of the board stuffed. Which is, hindsight being 20/20, I should have done that at the beginning. The other thing I learned from this design doc is I should really have the antenna part of the SOM sticking off the board, because we're interfering with the, and that makes sense. I've done some RF in my day, so it also recommended that. So I'm going to slide the CPU off, and that'll give it greater reliability and range. So the other topic I want to talk about at work, I'm designing the with the team the main computer for the Archinaut 1 robot. We have to use an FPGA because it is rad tolerant, and rad tolerant microprocessors are pretty pricey when you can get an FPGA and pretty much do whatever you want. You can put a CPU core inside, and you can write fabric code so it runs in parallel. So we're using an FPGA. So I'm very submersed into FPGA technology. The key things for FPGAs, they're easy to build massively parallel processors. When you write code for an FPGA and tie it to an I/O line, basically that I/O line is being run by its own customized little processing unit, processor, completely in parallel with all the others. So you could be, looking at sensors and running motors and everything else, and each device has its own dedicated 200 megahertz processor that's doing exactly what is needed for the device. So it's not implementing a whole instruction set and everything else that you need for a micro. It's just doing it. It's creating a custom circuit.
So it's like you're combining all the I/O into this programmable gateway.
Right. So, you might have, the part that we have has about 200 pins. So when you write the Verilog code or VHDL, you write a little process, kind of like the way you'd write in any language, but the tools actually create a custom logic unit that is running that pin, and then you can have some sort of bus or some other hierarchical structure inside the chip that's controlling everything. I'm a big fan of hierarchical control systems, so.
That gateway manages all the I/O pins, right?
Yeah, it's basically you're building a massively parallel computer. Yeah, each one of these processes can run at 250 megahertz independently. There's no interrupts. You know, normally in a regular microprocessor, you have to do multitasking, which means, because the processor can only do one thing at a time, although very fast, what happens when you have asynchronous devices, let's say you put them all on interrupt pins. Well, you can have states where this interrupt comes in just at the same time as this other one, and they're different priorities, and you don't get the behavior you want, you know, and it's really hard to debug stuff like that, you know. When it works 99% of the time, don't you hate that? So with an FPGA, it decouples that sequential processing and multitasking into very simple, massively parallel processes. And there's no interrupt issue. There's no interrupts in the system at all. So, longer term, robots are massively parallel systems anyway, right? If you have, if you're building a humanoid robot, you got 7 degrees of freedom on each arm and maybe each leg. You know, each one of those degrees of freedom, which means a motor, you can equate DOF to motor, has to be intelligently run simultaneously to give the robot smooth motion. You know, it's really not a job for a microprocessor. FPGA is just perfect for to build intelligent robots. So with FPGA, when I think of RTL, which is register transfer logic, I think in terms of the more primitive way of programming FPGAs in either Verilog or VHDL. If you look at the code, you see a lot of bit manipulation. It's kind of in the weeds. It's not at a high level of abstraction. Dr. Ting has made a wonderful fourth processor, and you know, you can, you know, there's quite a bit of code to implement that. So when I first got into FPGAs is in the 90s, and during those days, that's the only way you could program an FPGA. So they said, you know, we want to be more like the programming languages of a microprocessor, you know, like Forth or C or Python, whatever. So the higher level of abstraction you can get when you're programming, you know, you can focus on the algorithm rather than the details. So you don't get lost in the weeds so much. So they started developing what's called behavioral hardware description language. And so in VHDL, it's called behavioral VHDL. In Verilog, it's called system Verilog. So the idea with a behavioral type hardware description language is you can code it at the algorithm level, just like you can in C or Python or C++, whatever you want. So that's the goal of going with the more behavioral type programming. So you can easily build very complex systems using these techniques. Since 1990, VHDL was the preferred language for FPGAs. But interestingly, the ASIC guys preferred Verilog. And the reason is Verilog has a lot more support for very finite timing. So you use these languages not only to synthesize inside the FPGA, but you use the same language to build a test bench that will exercise the input to your circuit. So the idea behind a test bench is you create a motor control circuit, and then you write this code that toggles the pins at different patterns, and then it can also capture the output, and then maybe display in a terminal, what's going on. So it helps you debugging. Verilog has a much more powerful language, you might say, for this timing aspect. So the ASIC guys really want to understand the timing inside their chips, and so they preferred Verilog. The FPGA people, it's just one of those things. Like the idea of VHDL was kind of like, it was a derivative of Modula 2, I think it was, right? So, it's kind of Pascalish, but it's very wordy, very wordy type language. And Verilog is very short and sweet. In fact, Verilog is modeled on C, so it has C syntax. So both Verilog and VHDL has been working up to more behavioral level type capability, and System Verilog has a new standard as of 2017, and it is very powerful. I'm going to show you some code snippets here in a minute. This book is a must-get if you want to do System Verilog. Now it says RTL, so I think in terms of RTL as describing the lower level way of doing things, but anyway, his is all about System Verilog, but he uses RTL in the name of the book. So RTL modeling with System Verilog by Stuart Sutherland, and he was actually on the 2017 standards team. So it's and I found so far with Microsemi Libero tools, it implements all the 2017 constructs. Very powerful. So I've been reading online that System Verilog for new projects is kind of the preferred way to go. Made in Space, we're focused on System Verilog. So here's an example of System Verilog code. I'll show you a few examples. So you do a tick define. You'll notice this is very much like C. So tick define, the data bus width is 31. And so you do all your pound defines at the front end, create all the widths of your buses and that sort of thing. And this way, let's say you want to go from, let's say we build a fourth processor in System Verilog, and we have a bus width, and we have an address width. And so the bus width is 16, and the address width is 16. And then we say, oh, we want a 32-bit and a 24-bit. So you just change it there, and then when you resynthesize the code, it just builds exactly what you want. Very powerful. So the largest piece of code in the highest in the hierarchy is called a module. So with the module, you define all the inputs and the outputs. System Verilog, if you look at standard Verilog, you'll see that it says input and it'll say reg, R-E-G, register. With System Verilog, it's doing some more functionality, so you want to use the term logic. So wherever you'll see tons of Verilog code out there with reg. So you want to start using logic. Now, I'm defining the data bus. We'll see what I did. You have to put a tick in the front with System Verilog. But anyway, this is the address width. So remember I defined that as 31. 31 is really 32 because it's going down to 0. So you can see that if I change the pound define at the top end of the file, it's going to change the width automatically throughout the code, just like pound define does in C. So these are defining registers within the system, and you see I'm doing the same thing here. So now all my registers will change. So I've defined my inputs and outputs, and the pound define, you know, tells the system that it's 32 bits, 16 bits, 24, you know, 63, whatever. So anyway, this is defining registers. The assign means that, and you can have some like you can add things, or you can put a you know, some math right in here. You can put a you know, have it do something, not just assign a value to it. But anyway, assign means every time you see assign, it's creating a wire, and it's running in parallel. It's doing all this in parallel. So this is, remember I talked about a process. This is how you define a process. You define an always. Now in system Verilog, in regular Verilog, you'll see always statements. You won't see underscore FF. With system Verilog, there's basically 3 types of circuits that we're building. We're building digital. We're building, you know, clocked digital. Please underscore FF. If you're building combinational, which between the 90s and 2000s, all the big manufacturers like Xilinx said, don't use combinational logic. Combinational logic works, but the problem was if they changed the speed of the FPGA and you didn't write your code properly, and you were kind of expecting this process to finish at a certain time over this one, and they changed the FPGA, and now it switches, it breaks your code, right? So they always said, you know, use clocked logic. But nowadays, if you're smart, use things like semaphores, then you can get around that. So anyway, there's an underscore FF and there's an underscore COM for combinational logic. And then pos edge just means positive edge. We're going to do this. It's a simple counter routine. So the counter is incremented, and if the counter is 0, then I invert this. This goes, on my dev board, it goes to 2 LEDs. So if you set the counter, say, to 24 bits, 26 bits, it's blinking at about a second with this code. If I set it to 12 bits, right, then it's going to blink, you know, that much times faster. So if it's 26 bits, it's 1 second. It's 25 bits, it's a half a second, that sort of thing. So if you're building a robot, you're going to have each always statement is going to be running its a separate motor, acquiring data from a sensor or whatever. And they're all running simultaneously at whatever the clock rate of your system is, which is typically like 250 megahertz. So they added in System Verilog enum, so the C enum. It's a little bit different, but anyway, the idea here is we're building words, right, that allows us a very high level of abstraction in our programming. This is very cool. So they've added type def struct, so that this is a kind of a defining word in C, you know, creating a structure. And so it created an 8-bit field here, and then the joint data size, which is, I think that's defined as 16-bit. So it creates this, you know, 2 fields within this structure. And we call that ARM command data T. So that's it's almost like a create does sort of thing. And here, see what we're doing? We're defining a new object structure, which we call ARM command packet. So now the other interesting thing here is we're making an array. So if I have 7 degrees of freedom, I make this a 7. 6 degrees, I make it a 6. Remember up at the top. So now we're creating this structure and an array of structures, which really is nice for making it high level. The other thing that System Verilog adds is function. So this is a function. Functions work a lot differently in FPGAs than they do in a microprocessor. You think in terms of, you write a function and it compiles this code that gets called all the time, right? Called by different places in your code. That's not exactly what happens with an FPGA. Basically, when it sees a function, it's going to actually create a new circuit. But it's going to allow you to program at a high level. From a high level, it's going to work the way you think it is, like calling a function, but it's really creating a little circuit there of this function. So you can see with this, so I have a function called load velocity that I call, and basically we have a packet over say an RS-232 bus, which maybe has 7 16-bit values. So that's what load packet does. It loads that into a buffer. And then we can use, just like C syntax here, we can make a for loop. And begin, end is like the curly brackets. And then this is kind of cool. So the ARM command packet with the I, so that's going through the array of structures and we're doing processing a PID on those with one line of code. And then we're going to add to those values, we're going to add an offset torque, which is another array. So we've done a lot of stuff in that little bit of code, right? It's very high level. So this will be something that happens after, we get the boards done and running and all that. So maybe second half of next year. But, start with Dr. Ting's FPGA 4th engine, add some RAM and flash, and some driver circuits. Maybe we use the same circuits that we designed in the F32 controller. And we can start playing around with FPGAs. It's nice having a sequential processor in the FPGA. So people, like at work, we're using a RISC-V processor. But I am pushing almost all the control code into the fabric, using System Verilog. We're doing some pretty high level, control stuff. And so far it's working out very well. So that's kind of where I want to go in the future, long term. And then, of course, we'll add the Triune OS. And my interest in all of this, my long-term interest, is to design AI for intelligent machines. And I think that's where we could really get some excitement in the group. We start doing that kind of stuff. Some of you super programmers can start, adding a lot of intelligence on top of this thing, and we could make something that's, world-beating. I think that when we get real hardware that works, it's going to create a lot more interest in Forth. I think Forth will really take off. I really do, because I programmed robots in a lot of different languages, and Forth is the only one that really supports AI properly. My opinion. All right, so I want to finish up with our, so Made in Space is all about manufacturing in space. We're going to be manufacturing with autonomous robots in space. And I'm on the team, the avionics team, working with 2 other people on it. They're the team leaders. I'm the guy that's working on the actual hardware and software to make the central computer work. But the goal is to manufacture things in space. Manufacture solar panels, manufacture crystals, manufacture fiber optic cable. When you manufacture crystals or any sort of thing like fiber optic cable in space, you get a much pure, clearer cable. So you're going to have much higher bandwidth from a fiber optic cable made in space, and you're going to have a lot more range. And I believe that next year we're setting up our fiber optic cable manufacturing facility to the space station. We started making payloads for the space station. Company's about 9 years old, and heavily funded by NASA. We have some DARPA projects. NASA loves us. The idea is, you know, you could build a solar panel, put on a rocket, haul it into space, and solar panels are big, right? So that costs a lot of money. Well, how about just take a spool of material, fly into space, and make the structure for the solar panel in space? I haven't seen this video, so it'll be. That's our president. What's going on? I wonder why it's not playing. What's that? Yeah, hang on a second. Yeah, hang on. Let's see. Yeah, I'm working on it. I have to bring up my audio settings. Stupid Windows can't figure it out. Yeah. The what? Not on my TV at home. This one here?
Yes. This one. Plug this one in.
Other sectors with an era where, you know, rely.
You'll want to put the microphone up next to the speaker.
To me, and a special opportunity to speak, because about 4 years ago when I first came on, Congressman asked me to come and speak, and it was like his very last keynote, so his very last day, and I was quite nervous. Didn't do the best job, so it'll be better than last time. So, just as a brief overview, Made in Space is an in-space manufacturing company. We're known for being the first company to ever successfully manufacture functional objects off the face of the planet with a 3D printer on the International Space Station in 2014. Since then, we've really expanded the portfolio of in-space manufacturing capabilities on orbit. We launched a second generation machine in 2016. We launched a Z-Blade manufacturing device a couple of years ago. We've operated that several times now, and really expanding our capabilities as humans in doing in-space manufacturing and assembly in space. So why does this matter? In-space manufacturing matters, simply put, because it gives us a reason to go and stay in space. And that's really core to the sort of fundamental vision that we have at Made in Space, and I think many companies that are represented here today have, which is that we want to see people sustainably live and work in space. I always kind of joke that I want to see people with boring jobs in space, because that's a great signal that we've successfully expanded our economic influence into this great frontier. And I also really think that in-space manufacturing, manufacturing in space more generally, really leverages, stands on the shoulders of giants of the successes of other sectors within the space community. We live in an era where, reliable, reusable rockets are commonplace, right? I have a colleague of mine who has 2 small children, and those children will not get out of bed to watch a launch unless there is also a return associated with it, which is, just totally like a really weird, thing to think about. We live in an era of mature small sats, right? That are essentially built on the successes and the evolution that we've seen in electronics, driven by things like laptops and smartphones. We even live in a world now where there are like multiple, legitimate, technically hard-nosed companies that want to build commercial space stations. They want to build the successors to the International Space Station. And all of these things both enable us to go and stay as a species, and will be leveraged, and the potentials of them will be unlocked by the synergy with in-space manufacturing. If we think about, our friends at Axiom Space or Bigelow Aerospace, these commercial space station providers, what's the one thing that they really want? They really want creditworthy tenants who will be there, be able to buy a portion of their module or lease a portion of their module and operate. And in order to do that, we need profitable, we need to be doing things that are profitable in space. Tourism is really amazing, and I believe will be an important part of the commercial low Earth orbit ecosystem. But manufacturing in space, processing of materials in the microgravity environment, that because they're processed there, they have new and interesting properties and are valuable and are profitable to launch, do some process in space and then return down to Earth to sell into our global markets. That really is, to me, the anchor tenant for commercial space station operations. I'm not going to talk too much about that today, but that is an area that we and many other companies are pushing really hard on, right? Like we've built and launched a device to manufacture Z-line optical fiber, which has a 10 to 100 times better signal loss than traditional silicon fiber. We've done that. We've operated the device several times on the ISS. We're building a second generation of that device to launch, in the coming year or so. There are other companies that are working on things like bioprinting that might enable us to make, heart valves one day in space, and other things like that. There's also companies working on, high throughput research to do in space. Taking what we might do for drug discovery on the ground, doing that in space, and adding to our, our collective knowledge and consciousness that way. Another really interesting area, though, about in-space manufacturing is manufacturing assembly of satellites in space. That every satellite we've ever sent to space, we've done it the exact same way, right? We fold it up, we fit it in the top of a rocket, we blast that rocket into space, and subjecting our payload to a really high G environment. It gets to space, it unfurls itself, and then it operates for 5 or 10 or 15 or more years in this this very mechanically benign environment. And that's really, really cool. That's that rocket ride is the reason that my colleagues' kids get out of bed in the morning to see, as long as there's a return. But it's inefficient, right? Because we design our satellites to survive that rocket, rather than optimizing our asset to function in its operational environment, which is fundamentally appealing to us as scientists and engineers and even humble recovering lawyers. And but in order to actually do that, that's where in-space manufacturing and assembly comes in. Is that if we launch raw material and a hardware manufacturing platform in space with our satellite to manufacture things like large antennas or large solar arrays, we can make those really delicate things not have to survive the launch loads, and we can make them in an efficient and an optimized way for the space environment. Now, and this is really important, because what I think that one of the things that we've seen over the last decade with the sort of the evolution of the launch industry is that we've gotten really good and we've gotten more efficient at launch. The price has gone down a lot, but we haven't seen necessarily a similar, we haven't seen a similar spike in new launches. The pie of launch has not doubled when the price dropped in half. It maybe expanded a little bit, so we're just kind of slicing this pie thinner and thinner. But things like in-space manufacturing of goods and things like manufacturing satellites in a way that's optimized for space, I believe will actually, will expand the pie. Will expand our pie, the pie of operations, expand the pie of launch. So maybe just to, articulate this a little bit more. Historically, we live in this world where maybe a Falcon 9 costs $60 million a show, and we put a satellite on top of that that costs like hundreds of millions of dollars, and it produces kilowatts of power to do its scientific, to do its mission. We'll get into this a little bit more in a little bit detail in a moment, but in-space manufacturing and assembly, on-orbit manufacturing, potentially allows me to launch a satellite that that has a mass that's a fraction of the satellite you put on the Falcon 9. But provide it the same class of power, give it kilowatts of power, maybe even 10 or more kilowatts of power, but on a small satellite bus. So now we're launching a satellite that maybe costs tens of millions instead of hundreds of millions, and we're putting on a rocket or putting on a ride share that costs $5 or $10 million rather than $60 or $100 million. So I think this is a really important shift, because right now what we're doing is taking a $100 or $200 million asset and we gave it a discount. We put it on a $60 million rocket. But what we have an opportunity to do is take that same capability and lower that price even further, and to tens of millions, to knock off a zero, and also put that on a rocket itself that's in a similar kind of class of cost. And that kind of savings really has the potential to expand the pie in terms of the different kinds of operations that we can do in space with satellites. And in-space manufacturing and assembly, I really think it opens up an incredible future, where from low Earth orbit out to deep space, as we can kind of see in this picture. In low Earth orbit, we have satellites that, if we're enabling things within space manufacturing and assembly, look really different than the satellites of today, right? You look at some of these concept images, and you just kind of like try to think about how we might do this in a traditional launch sense, and it becomes very, very difficult, as well as doing things like manufacturing material and microgravity. So how do we actually get here? What are the actual, what progress is actually being made on this? So at Main Space, we think there are 5 key steps, 5 key pieces to being able to do in-space manufacturing and assembly. The first piece is that you have to be able to manufacture in microgravity. This is something that we've been doing, as I mentioned, since 2014. That's a picture of Commander Butch Wilmore on the International Space Station holding a fully functioning ratchet that we manufactured in one print in response to a need that he had on the space station about 5 years ago. The next is you need to be able to do this manufacturing in the vacuum of space, in the thermal and vacuum conditions that you're going to experience in space. We also care about things like radiation. The third piece is really, really important, because typically when you think about manufacturing anything, you kind of, and especially with 3D printing, you kind of think of a big box that chunks up things that are smaller than itself. And that's really cool, that's useful on the ground where we have lots of space, and mass constraints are not really a huge factor. But when we go to space, we're probably not going to launch like a 50-meter 3D printer space and chunk out like 20-meter reflectors. We want to launch something really small that can make really large things. So we developed a technology that we call ESAN, Extended Structure Additive Manufacturing, that can do just that. Can make it from a small box. It can manufacture arbitrarily large structures. In fact, we have a structure in our office in California that is 37.7 meters long. It's longer than the solar wings, than a solar ring on the International Space Station. And the reason it's that specific length isn't because, there's some geeky, elite speak thing going on there. It's actually because our building was that long. We ran out of space to make that, to keep going. And of course, the next piece here is that it's not good enough just to be able to make things in space. We need to integrate those and make them useful. So that's where robotic assembly comes into play. There's lots of really good folks that are really talented with robotic assembly. We put a heavy emphasis on not only being able to do it, but being able to do it in autonomous, repeatable, and recoverable fashion. Because things don't always go the way you want them to go exactly, and you want your system to have a little bit of smarts to say, hey, I've encountered a problem, I'm going to stop, and I'm going to call home, and I'm going to say, what do you want me to do? Or, and also suggest a method for potentially recovering the operation. And finally, you need to be able to verify for yourself and for your customer that what you've done, that you did what you said you were going to do, which is where inspection and verification comes into play. So putting all these pieces together, we've been working on these pieces for several years now, and we put these pieces all together into a kind of platform, a general manufacturing assembly technology that we call Archinaut. We specifically chose to make Archinaut and to have the sort of design language and thoughts behind it be general rather than specific, because we wanted this kind of paradigm to minimize the NRE between missions. But the same robotic system that assembles a solar array could be used with could be used to assemble a reflector, or could be used to assemble a radiator. That's also beneficial because it means that we're getting, the heritage that we're getting on this manufacturing assembly subsystems is increasing with every mission. The changes are minimal between missions, compared to something that might be more specific, like a point solution for building like a really amazing L-band reflector. While that may be a little bit more optimized, you lose the potential benefit of having a more generalized tool in that regime. So, as I mentioned, we've been operating on the International Space Station for a couple of years now. We were fortunate enough to receive a tipping point contract from NASA a couple of years ago to start burning down the technical risk with these programs, culminating in a series of TVAC tests to first show the ability to do in a TVAC to manufacture extended structures, and then to about a year later do robotic manufacturing and assembly in that TVAC. But we all know that we're in like a relatively conservative industry, right? And we're all willing to fly anything as long as it's flown once before. So how do we get over that hump? Well, the way we get over that hump is again, fortunately, partnering with NASA via public-private partnership to actually design, build, launch, and operate the world's first satellite that will manufacture and assemble portions of itself. And that satellite is this guy right here, Archinaut 1. It's a very Silicon Valley name, Archinaut 1. So this is a definitive demonstration of the ability to do manufacturing and assembly in the space environment. Right now, this is looking to fly in 2022. It's a small satellite, weighs about 200 kilograms. And you'll see on that small satellite we have two very, very large solar arrays. And you'll see in the middle there these two sparse-looking spars. Those are actually manufactured on orbit. We'll stow on the interior of the satellite assemblies that contain these rollable solar arrays. And when we get on orbit, we'll robotically remove those, put together that assembly, and position it so that we can manufacture one of those long spars, creating a solar array that's about 10 meters long and about a meter wide. And then we'll flip all that around and do that same process going the other way. So once this is all manufactured on orbit, will get about 20 square meters of surface area on orbit, which is substantially more surface area than any small satellite has deployed in the past. And on this mission, if you use kind of state-of-the-art solar cells, like things that exist right now, we could generate 5 to 8 kilowatts of power. Whereas the state-of-the-art, the sort of flown, demonstrated state-of-the-art on small satellites is, maybe like 1 kilowatt of power. So we're talking like 5 to 8 times the state-of-the-art being demonstrated here. And that's a really, that demonstration is fundamentally, shows that we can fundamentally do this in space. But it's not just about building, it's not just about providing big power for small satellites. This is a generalized capability. That same device that can manufacture those spars can be used to manufacture antennas. The same robotic arm that's going to assemble those solar array boxes can be used to put together, to put together radiators, to put together big reflectors. And this is really about eliminating two constraints that we have on spacecraft today: volume, volume and mass. That for every spacecraft that we send up, because the mass of those spars that we're going to manufacture on orbit is significantly lower than than comparable deployables that you would buy off the shelf today. All right, well, there we go. So to kind of close out on a couple of specific near-term examples of this, Archinaut 1 is going to definitively demonstrate this technology, but it's also a platform that provides a significant amount of payload space on the front of it. That we're flying a payload on it for the first mission. There's a high power payload to use the amount of energy that spacecraft provides, but this same platform, it almost serves as a next generation satellite bus for small sats, where you can say, hey, do you need a lot more power because your sensor, because we have these high power sensors now that we're flying on large satellites. Maybe we want to fly those on smaller satellites so that we can take advantage of lower launch costs to get a similar capability to space. That's enabled by Archinaut. To show, again, to illustrate like the sort of broad-based technology that exists here, the broad-based enabling technology that exists here, this is a picture of a ground-based mock-up of a structurally interconnected interferometer spacecraft that we call Optimax SCI. So this actually manufactures two about 10 to 20 meter long booms to do interferometry in low Earth orbit to spot near-Earth asteroids. The same ESAM that's flying on Archinaut 1 lives inside of this and enables this kind of mission. Similarly, really large reflectors like we see here in these pictures, 10 meters plus, also enabled by the ability to manufacture and assemble with Archinaut. Going on a little further, it's really exciting that MEV-1 is launched. Our first commercial satellite servicing mission is now on its way to GEO. And that mission, but satellite servicing really could be enabled by including manufacturing assembly on those assets. So not just talking about refueling or shaking a solar array so that it pops out, but augmenting and adding structure and adding sensors to those assets to extend their lives, to get more to a paradigm where satellites aren't sort of fire and forget, but the satellites themselves are reusable and repairable and extensible. So in closing, we're really like the early stages of in-space manufacturing assembly, but I truly believe that this technology will be as paradigm shifting and revolutionary for satellites as reusability was for rockets. And thank you so much for your time.
Thank you, Henry. We have a few questions from the floor. First of all, we need to get a copy of your charts without the proprietary markings on it, because we're going to publish all the charts. Sure. And we don't want to have them on our website with your proprietary. That would, the lawyers get nervous about that kind of thing. So, number one question people have asked: explain the cost better when manufacturing material has to be shipped to space, which is a costly supply chain.
Yeah, that's a great question. So The near-term cost benefit is around sort of dollars per capability, right? Like the ability, delivering 5 to 8 kilowatts of power on a small sat is perhaps achievable with deployable technologies, but it's really, really, really expensive to do that engineering. This is a much simpler approach, and you do get additional mass savings because the structures that we manufacture on orbit are generally significantly lighter than the deployable structure that you have to send. So there's 2 vectors there that provide cost savings.
Okay, well, to follow up on that, what are the sources of the raw material for the Archinaut construction?
Yeah, so in the beginning, the raw material we brought with the satellite. So Archinaut 1 will contain feedstock spools within it that will be launched with it, and then we'll do the manufacturing with that material.
Okay, with space debris becoming a bigger issue, would you work toward not so much biodegradable but space degradable materials?
That's an interesting question. It's an interesting question and worth like some advanced concept exploration. I think that in the more immediate term, we're more focused on complying with with the sort of good neighbor policies of having your spacecraft last below a certain number of years in low Earth orbit.
Good. Okay. Will you do you plan to manufacture medicines in space? If so, who would regulate that manufacture?
Oh, that's a good question. Certainly, that's something we've looked at. I think, in particular, for long-duration human spaceflight missions, those sorts of approaches are important. I think the same regulatory structures that exist for human spaceflight right now would be applicable.
Okay. The most popular question today is one that my father would tell me is a rude question, but I will ask it anyway. Who is your biggest customer?
Currently, our biggest customer is NASA.
Okay. And second like that?
What happens when you win
Yes.
the first satellite we've ever had?
When will Made in Space make money?
So we've been profitable and growing every year that we've existed. We do not, for a very, very long time, we did not have any outside investors, and we've actually doubled in size about every 18 months to 2 years.
Good. So a couple of questions regarding materials. What materials are you manufacturing that can handle the thermal and radiation environment of low Earth orbit?
It's a really good question. So, and the subject of a lot of research that we've done over the past several years. So, one material that we've demonstrated on the space station is a polyether imide polycarbonate composite called Bolton. That's a polymer that we manufacture pretty routinely. It's actually flown on some Air Force birds as well as a lot of NISI experiments, and it holds up well in the vacuum as well as to the radiation environment.
Is that what you use to print antennas with?
So antennas require a certain amount of metallization or some conducting thing. There are a couple of different. So that material is something we could use as part of an antenna. Yeah.
Okay. How do you validate the structural integrity of your manufactured structures on orbit?
That's a good question. So the first way that we'll do it is, there's a lot of manufacturing on the ground, and the goal is for the manufacturing equipment to work the same on the ground as it does in space. We validated that approach on the International Space Station. The printers that we have on the space station operate like the ones when they're on the ground, and we do comparisons there and haven't found significant differences.
Super. Could this technology be useful for making robotic landers in space for missions to the moon and Mars?
Yes.
Softball question, right? Have you attempted 3D printing of human tissue for medical purposes?
We have some internal research and development efforts around bioprinting.
Good.
I'll just leave it at that.
Good. Do you see your approach as being exposed to cybersecurity concerns?
That's, I think, a concern with any electromechanical device in the world or in human dominion. So yes, that's a concern.
Okay. How do you manage heat dissipation when printing the larger structures in space over an extended period of time? Yeah,
no, it's an interesting problem because you can kind of look at that wing and say, well, you're creating this like cold or hot sink as you're manufacturing more and more. So there are within the manufacturing volume itself, we put a lot of effort into keeping the thermal environment there within a very narrow band.
Okay. Have you considered using additive manufacturing on orbit for deorbiting purposes for the end of life for satellites?
Yeah, we have looked at that on a couple of different occasions, for manufacturing things like drag sails, for instance.
Wow, great. Let's see, can you restock with the raw materials after the initial stock of build materials is used up?
Yeah, so that's one of the things that's really interesting about sort of Archinaut infused assets, right? Is you have this residual manufacturing and manipulation capability that if you resupply that or restock that, you could have it reconfigure itself on orbit. So that's absolutely something that we build in.
Super. Here's a very popular question, not necessarily posed in this session, but it comes up every time. Do you have any internships or scholarship programs for students?
Yes.
Okay. How do you apply? How it's set off?
Right. So for the summer, we're a member of Rick Owens. We're a member of Matthew Isaacsowicz, and then our general approach for our general solicitation for summer interns turns on like in December and in the December-January timeframe. We also are interested in co-ops throughout the academic year.
So you have a web page or something?
Yeah, you can go to mainspace.us/careers and find the information there.
Good. Who do you consider to be your biggest competitor?
It's a good question. This is an area that increasingly folks that are really, really capable and much larger than us, and folks that are also, kind of some, that are smaller than us care a lot about. So former Orbital AFK, we have a lot of synergy with them in this area. I guess it's Maxar now with SSL. They're very focused on assembly in space. Those are two companies that we sometimes work closely with, and sometimes we're kind of going after the same thing.
Is additive printing a reversible process? Can you unprint it and reuse the raw material if needed?
So we are launching on the next Antares flight to the space station. We're launching a commercially sponsored polymer recycler that will take not only old 3D printed objects, but other waste plastics, and recycle that and turn that into 3D printed filament that then is compatible with our printers on the space station, creating this almost closed loop manufacturing and recycling environment.
Can your printer print a printer? There's a scary question.
Yeah. So not yet, but actually the very first object that we ever manufactured in space was a replacement cover for the very first printer to demonstrate that there is some inherent self-repairability quality to this technology, and also to show why this is something that we really went after, because it's a general manufacturing solution.
I, for one, welcome our robotic overlords. Do you see any benefits on adding humans in the loop now or later to increase quality assurance and quality control?
Our emphasis has been on actually trying to take humans out of the loop to try to make the systems more autonomous because of the high cost of having humans in the loop, both from a telerobotic perspective or from having them literally there in space. Certainly, having people monitor those processes and ensure that they're operating is very, very important, but we think that autonomy ultimately will make these things more cost-effective.
Wow, thank you. We are out of time, and despite the fact that the team keeps issuing questions, we're out of questions. Thank you very much.
Thanks so much.
Thank you.
That concludes my talk.